All right. Hello, everyone. Good morning. Thank you for coming to the manipulation session on a Friday at 8:30. Woo! Great job showing up. We're very excited for everyone. And our first speaker today is going to be Tilda, presenting their work on, our first presenter, it's so early. Zealand should be presenting on Tilda, teleoperation for dexterous in-hand manipulation learning with a delta hand.
Okay, thank you. Hi everyone, morning. I'm Zilin, and today I will introduce Tilda teleoperation for dexterous in-hand manipulation learning with a delta robot or delta hand. So dexterous manipulation is crucial for wide-range real-world applications, and humans are extremely good at this. Such as we can do small components assembly, we can pick out pills from medicine box, or we can do various cooking skills. However, if we want to enable robots with human-level dexterity, it requires both precision and robustness on hardware and software. Thus, we are motivated to introduce Tilda, an imitation learning-based in-hand manipulation system. Our system includes a dexterous robotic hand, delta hand, a teleoperation interface, telehand, and we leverage diffusion policies for imitation learning. So given a task, the human teleoperator can first teleoperate the telehand and collect the demonstrations with the delta hand. These demonstrations are used to train the diffusion policies. And during the inference, given the in-hand camera images and the joint states of the delta hands, the learned policy can predict the actions. The delta hand is a highly dexterous hand with 12 degrees of freedom based on the delta robots. And the delta robots uses closed-form kinematics and thus is really simple to control. We 3D printed the finger and the fingertips of the delta hand, so the whole hand is compliant to adapt to the environment and robust to the policy deviations. And the whole hand structure is modularized, so it's really easy to configure and to maintain. We also additionally add an in-hand camera to provide the visual in-hand observations here. For teleoperation interface, we introduced the telehand with a kinematic twin design. So kinematic twin means that the telehand has exactly the same kinematics model and the hand configurations compared to the delta hand. And as the human teleoperator moves the telehand's finger, we can see the delta hand's finger can precisely and smoothly follow the motion here. For the telehand kinematics design, it has several benefits. First, it enables really precise mapping because it uses a direct one-to-one joint position mapping. And secondly, it's super user-friendly. Human can just move and grab the telehand's finger. And we are using the ROS to do the real-time interfacing between the telehands and the delta hands. All of these features make it really efficient to collect the high-quality demonstrations. And here we show the working principles of our teleoperation interface. The telehands can be manipulated by the human teleoperator, and the potential meter on the linear slider can record the joint positions. These can be further mapped to the delta hands linear actuator with a PID control. We evaluate our system on 7 tasks here. It has in-hand translation. We can see here the block can be slid horizontally on the table, or we can do the block lifting from the tabletop to the air. We also have in-hand rotation. We use the fingers to hold and rotate the ball, or we can twist the cap to open. We're also able to grasp the object with complex shape, or we can do forceful articulated object manipulation. Here we use 2 fingers to hold the syringe tube and the other 2 to push and close the plunger. And additionally, we show the shape insertion task with multimodal action here. This requires coordination between different fingers to transport the object. Additionally, we demonstrate the challenging tasks here. First one is a diamond shape block insertion. This requires more than 90 degrees rotation to match the block to the template. And we have the finger gating in the air. Here we use 2 fingers to hold the ball firmly and the other 2 to rotate the ball. And last one is a block sliding in the air. The block is initialized on the table and we use the fingers to pinching and sliding the block to the air. And on average, we can achieve over 90% success rate across all these tasks. If you'd like to learn more about this work, please visit our project website or stop by our posters. Thank you.
Thank you very much. That was awesome. Any questions?
Thank you for the interesting presentation. So you've made some different choices relative to some other teleoperation systems, like moving the fingers in the telehand instead of kind of having the teleoperation being an extension of the human hand and try to demonstrate. What do you think is the advantage in what you're doing relative to some of the alternatives?
So your question is about like we are doing different like teleoperation, right? So I think the intuition behind that is humans are good at using tools. So we tried to directly mapping the human finger to the robotic hand before, but we found like it's super hard because our hand is not exactly the same like shape as a human hand. So we need to find an alternative way to do this teleoperation more like natural for the human. So with that, like our telehand is more like a tool as a like intermediate step. So human can be more like natural to teleoperate or like to manipulate this tool. And then this can be used for the teleoperation and on the robotic hand.
So you're planning perhaps a human study as well of figuring out what are the most natural interfaces?
Yeah, that's a great question. So we are actively working on that part. Yeah.
Great, thanks.
There's one up there.
Hello, thanks for the presentation. I'm wondering, for the demonstration, first, how many demos normally do you need for one particular task? And second, do you have to actually perform very consistent demos?
Yeah, thanks for your question. So for the first one, I think it depends on the task. Like for some tasks that has repeat motion, for example, the sliding or lifting, it will require definitely less demonstration, for example, 20 to 50. But for the task that's slightly harder, for example, the shin insertion, that turned out to be the hardest one to learn because the actions are not always consistent, as you said, yes. And we have to have much larger like demonstration sets to train the model. So for this shape insertion, I think if you want to reach a kind of good performance, I have to at least have 80 to 100 demonstrations here. Yeah.
Thank you.
Thank you, Zilin. Let's
Thank
move
you.
to our next paper. That is Hackman++, spatially grounded motion primitives for manipulation by Bowen and Yilin.
Thank you. Hi everyone, I'm Bowen. Today, Eileen and I will be presenting Hackman++, spatially grounded motion primitives for manipulation. Human-level dexterity requires both prehensile and non-prehensile skills. Non-prehensile skills include pushing, flipping, and so on. We often use a combination of these skills, like this example of organizing the carbonate. In our previous work from Core 2023, we show how to use non-prehensile skills to align 60 object pose. In this work, Hackman++, we move towards a more generalizable solution for robot manipulation. We propose a reinforcement learning framework based on spatially grounded motion primitives. It is able to perform long horizon contact reasoning, combining both non-prehensile and prehensile skills. It works on a diverse set of tasks, and it generalizes across objects. The standard action space in manipulation is often robot-centric. This is non-ideal for learning because most delta movements in the interactions are free space motions. It also makes the policy difficult to generalize across object shapes. To be more efficient and to encourage the policy's geometric reasoning, we use a context-centric action space where each action is a primitive spatially grounded on an object contact. More specifically, given a point cloud observation, we define the action space with 3 parts. A primitive location, selected from the object point cloud. A primitive type, such as grasping or poking, selected from a predefined set of primitives. A primitive parameter, detailing the primitive execution, such as contact orientation. Here's an example of a poke action being executed. The robot first moves the gripper tip to the selected location. It then pokes at the objects. After that, the policy selects the next action based on the new observations. By studying the commonality between tasks, we end up using 5 types of generic spatially grounded motion primitives. They are poke, grasp, move to, move delta, and open gripper. Collectively, they satisfy the needs of a wide variety of tasks. This action space is related to spatial action map proposed by prior work as a way of densely connecting actions to visual input. However, they are all designed with limited action mode and can handle only limited tasks. The other line of related work is RL with primitives or hierarchical RL. Some of them have difficulty with the joint optimization problem, while others are not spatially grounded. Heckman++ is RL with spatially grounded primitives and mitigates the aforementioned limitations while combining their benefits. It achieves object generalization and applies to diverse tasks.
Next, I will explain how we incorporate this proposed action space into a goal condition RL policy. We take as the input point cloud consisting of 3 parts. Here, goal flow gives information of the goal. Segmentation separates object from the background. We pass the point cloud into a segmentation-style actor network, producing per-point primitive parameters. We also have a critic network. Combining this with per-point primitive parameters, we get per-point critic scores. We repeat this for each of the primitive in the predefined primitive set. In the end, we get per point per primitive Q values. During execution, we select the primitive with the highest Q value. We evaluate our method on 7 simulation tasks with diverse object geometries. Here, I want to highlight our double beam task with 60 object pose alignment. The agent needs geometric reasoning to chain the primitives. For example, here, it needs to poke the box into a graspable pose before it does pick and place. We train our model on 32 training objects and shows that it can generalize to unseen real objects. Here are the rollout videos showing that we can do sim-to-real transfer with diverse object geometries. On the bottom left, for example, the agent is able to flip and rotate the toy car to reach the 60 goal pose. For quantitative results, we compare against 2 baselines. Both RAPS and PDQN are non-spatially grounded methods. They use regression, directly predicting a 3D continuous vector as a primitive location. Our method, however, is spatially grounded. The primitive location is selected from the observed point cloud. Our method, the orange bar, achieves reasonable performance across all the tasks. For easy tasks with limited object diversity, all methods perform well. For the rest of the tasks, it requires precision, long horizon, object generalization, or a combination of these factors. Our method drastically outperforms baselines. In summary, I want to highlight our contribution of introducing spatially grounded primitives. Our method generalizes over unseen objects. The learned policy shows both high-level reasoning and high-level planning and low-level motion precision. Thank you for listening.
Okay, thank you. We have time for a couple of questions.
Hi, great talk, thank you. I saw in the graph, or for the plots of the results on the RoboSuit pick in place, your method seems a bit lower than for the other tasks. Like, do you know why this happens, or do you see the failure mode for this?
Sorry, which seems to be lower?
Are you saying the pick and place task is lower than the baseline?
In the RoboSuit pick in place, yeah, it was on the previous slide.
Yeah, so we also observed that situation, and we conclude that the reason is actually because the RoboSuit pick and place does not require super high precision. You just need to place the object into the corresponding container. It doesn't need to be on an exact location. That's the first thing. And second, it's not like a super long horizon task. Only need just pick up and place it. And lastly, it doesn't really need much object generalization. It only has 4 objects in the task, 4 types of objects. This is why we found out it actually doesn't give much benefits to our method. Our method generally has larger advantage on tasks that require those 3 factors, which we talked about.
Thank you.
Yeah.
Another question over there?
Hello. Yeah. Thanks for the great talk. I think it's a really nice representation to select a point on the object where you want to manipulate. But how do you select on the gripper pose? Like, how the gripper pose should be oriented with respect to the point where you want to manipulate?
Yes, thanks for the question. So our action space consists of 3 parts. You mentioned that like, we have the location, and we have the primitive type, and lastly, we also have the primitive parameters. The parameter part is where we specify like how exactly the primitive should be executed, like where relative position of the gripper to the point we select, or the orientation of it. That depends on the primitive design, of course.
Thanks.
Okay, let's thank our speakers again.
Great. Next up, we have Bo presenting RoboPack, learning tactile-informed dynamics models for dense packing.
Hello, my name is Bo Ai. I'm glad to present RoboPack, learning tactile-informed dynamics models for dense packing. This is a joint work with Stephen, Haochen, Yixuan, Cheston, Yunju, and Jiajun. Imagine we want to place this object into this nearly full box. How would we do it? We would first look at the scene, try inserting it at different locations, finally placing it into the tray when we predict we can make enough space for it. This ability to integrate visual tactile sensing and make future prediction is crucial for many tasks. For instance, when packing a suitcase, we gauge the softness of clothing to determine the amount of force to apply. To enable robots to have a similar high-resolution tactile perception, we work with a soft bubble gripper sensor that provides sensor readings on the surface force distribution. And to integrate these tactile signals with visual perception, we propose RoboPack, a framework that integrates tactile-informed state estimation, dynamics prediction, and planning for manipulating objects with unknown physical properties. At the first time step, t equals to 0, we first obtain particles for each object in the scene via point cloud segmentation and downsampling. These particles characterize object geometry. To further characterize the dynamics properties such as deformability and mass, we append object-level latent physics vectors onto each particle, which are initialized as random noises at this point. We define these particles with physics embeddings as our initial state representation. Apart from visual sensing, we also obtain tactile feedback from the gripper. Using this initial state and the tactile feedback, we construct a state estimator that is able to infer the current state of the world with a recursive graph neural network at a later time step t equals to 1. And this can be done autoaggressively. Basically, at every time step, the state estimator refines the previous estimated state to produce an estimate for the current state using only tactile feedback. And this tactile-based autoregressive prediction enables state estimation without dense visual feedback. Basically, at each time step, we only require the initial visual observation to initialize the particles, and this effectively sidesteps the challenge of state estimation under visual occlusion. After we estimate the current state, we then use a dynamics predictor to evaluate different potential actions to take for model predictive control. And this dynamics predictor and the state estimator are trained end-to-end on real-world random interaction data by minimizing particle prediction cost. Next, we demonstrate that our framework enables adaptive robotic control. Here we are presenting the future rollout planned with MPC in the bottom right window. We can show that initially the robot intends to squeeze the object into the nearest row. However, during execution, it encountered significant resistance. Informed by the tactile signals, the model now realized that it's better to squeeze the object on the other side of the tray. Based on tactile signals, the model further predicts that we can push the object further to create more space for object placement. And this results in a successful execution using only one single visual observation at the beginning of execution. We demonstrate our method on various object configurations, including ones unseen during training time. Our learned models are able to generalize to objects with different shape, color, dynamics properties, and spatial arrangements. It can also be extended to other tasks that involve complex dynamics and partially observable physical states, such as non-prehensile box pushing. This task is much more challenging than a typical object pushing task because of two reasons. First, these visually similar boxes are constructed to have different mass distributions, and the unknown mass distribution makes the dynamics of the box highly uncertain. Second, as our gripper is highly compliant, the tool is only loosely held by the robot and can rotate in hand during physical interaction, making the interaction between the gripper and the box not very predictable. However, our method is able to leverage tactile perception to estimate the state of the box and figure out the most efficient pushes at every time step. Furthermore, we can even verify that the estimated latent physics vector during the task naturally cluster by box type. We can even train a linear classifier to predict the box type given these latent vectors, and the accuracy improves as physical interaction accumulates. This shows that, without explicit supervision on the latent space, our model naturally discovers meaningful latent physics embeddings through dynamics learning. And this tactile-based online adaptation enables our model to manipulate objects with unknown physical properties. For more information, welcome to talk to us at the poster session. Thank you.
Thank you. We have time for questions. There's one over there.
Thank you for the talk. Very interesting work. So I saw in your paper that you use MPPI to plan through these models. I just wondered, and I realize this is not the core contribution of your work, but I wondered if you find this to be sufficient to generate good plans, and also if you have future plans to try more complicated planners. Thank you.
Okay, so the question is regarding planners. Yes, we are using MPPI. I think with suitable priors about the task, for example, we assume that the motion of the robot is mostly on a 2D plane. It's actually pretty efficient to use MPPI to derive the control we need to achieve the task objective. In future plan, we can potentially look into uncertainty quantification and integrate that with theoretical guarantees from classical planners so that we can have a performance guarantee for our system.
Thank you.
There's a question over here.
Interesting work. So if I understood your presentation correctly, you're updating the latent state vector of the objects only using tactile information. But some things are, for example, the deformation of the third object in that row is more visually apparent than tactile. I think there's a chain there that you have to consider if you're only considering tactile. So can you clarify the design choice, or maybe I'm misunderstanding the setup? Thanks.
Sorry, so is the question about our state representation?
Yeah, I think that in your presentation you said you're updating the state representation only using tactile information. Is that correct, during interaction?
Yeah.
But some of the object properties are better inferred from visual information. For example, deformation, when you're pushing on that the row of objects, the last object was deformable.
Yes.
And that was visually apparent. But I don't know whether you'll be able to tell that from the tactile information if you're pushing on one end of another object. So I'm curious about whether you've thought about updating using both visual and tactile information or some other mechanism.
Yes, we think that for model-based methods, actually perception and state estimation pose a challenge on scaling up the method. One thing about visual perception is that it doesn't work so well for cluttered environments, for example, the dense packing task. So actually during physical interaction, the camera cannot capture the underlying geometry of the objects pretty well, since the objects are in contact. On the other side, tactile perception can give us a high-frequency feedback about the local interactions between different objects. And this actually complements visual perception pretty well. So our design choice is basically to initialize a particle-based representation of the scene, and then later on, we basically just rely on tactile perception to understand what is happening in the scene. So our tactile-based estimation not only estimates the physics properties of these objects, but also the geometry of these objects. So we found out that this multimodal approach to model-based control actually works pretty well. So I think that answers the question.
I guess I had a related question, which was, it seems like one of the powerful things about what you posed is you could include prior information into the physics vector. So you might have some prior knowledge about how squishy an item is, right? Which would then give you a lot of information as you forward predict. And I was wondering if you plan to leverage that. Like, I think you said you initialize it to random noise, the physics model.
Yes. Sorry, I think the sound is a little bit weak. So it's a question about the initialization of the physics latent vectors?
Yeah. Basically, could you encode prior knowledge into that physics vector?
Yes, I think it's actually pretty easy to encode. We can basically use an autoencoder to compress a explicit experimental vectors and use that as a particle attribute to initialize the process so that the models can later further refine the latent vectors based on tactile observation. Yeah, I think we can definitely incorporate such priors, and such priors can come from, for example, large language models or visual language models. And I think this is one of the future work we intend to do.
All right, thanks.
Thanks.
Our next speaker is Yiming Li, and he's presenting a paper titled Configuration Space Distance Fields for Manipulation Planning.
Hello, this is Yiming, and I will talk about configuration space distance field.
Closer to the mic, closer to the mic.
Sorry. The signed distance field is a popular representation in robotics for measuring distance between spatial points and surfaces, providing geometric information that can be easily combined with control, optimization, and learning techniques. It can also be used to articulate robots, where the distance is a function of both spatial points and joint angles, allows us to use the gradient with respect to the joint angles directly. Here we show a 2D case. The SDF reflects the geometric information nicely in task space. However, it's warped in configuration space. This is due to the nonlinear mapping between two spaces. And because of this, we have to solve many robot problems into separate steps. One is to plan in task space, and another one is to find the corresponding joint angles by solving inverse kinematics task with a few iterations. In this work, we propose configuration space distance field, and we call it CDF for short. Instead of mapping two spaces, we directly measure the radial distance from the current joint configuration to the object in joint space, corresponding to the minimum joint motion required by the robot to establish the contact with the object. CDF has the same zero level set compared to SDF, indicating the geometry of the object in configuration space. Differences lies in the non-zero level sets. CDF satisfies the Econo equation, which is a first-order partial differential equation with evenly spanned distances and unit L2 norm gradients that consistently point against the object. This property allows us to solve inverse kinematics problems through one-step gradient projection without the need of multi-step iterations, and is robust to any joint configurations. Additionally, it supports geodesic shorting, where the trajectory follows the level set in configuration space. It means that we can easily control our robot moving along the tangent space that keeps a certain distance to the object, which is particularly useful for motion planning tasks. Okay, then let's talk about how to compute CDF. An intuitive idea is to find all zero-level set joint configurations given an object, then finding the closest one to the current joint and compute the L2 norm angular distance. However, we don't want to compute it every time for new objects or dynamic environments. A smart way is to voxelize the workspace into a volumetric grid. For each point in the grid, we can pre-compute all zero-level set joint configurations. Given a new thing, we just need to verify which cells are occupied and fuse corresponding joint angles together and find the closest one for the distance computation. However, the volumetric representation still suffers from memory issues. To handle this problem, we can further encode it with neural networks for a grid-free and continuous representation, which also improves the computational efficiency and allows latent space operation. We conduct several experiments to validate our approach. The first one is a whole-body inverse kinematics task that lets the robot reach an object using its whole-body structure. CDF solves it in milliseconds through one-step gradient projection. It also allows find more solutions in less time compared to the state-of-the-art distance query-based approaches. We then demonstrate potential applications, such as the goalkeeper task, which requires the robot to find the joint configuration rapidly to defend a flying ball. Another one task is lifting a larger box using a whole body structure. CDF shows efficiency in planning time and also leads to a short angular distance. For motion planning tasks, we first show 2D results to compare CDF and SDF. Given the same obstacle and safety buffer, Our QP solver with SDF representation is easy to get stuck into the local minimum, while CDF successfully reaches the goal in many cases. We also conduct experiments for 7-axis robot in real world. The shelf environment highlights the capability of CDF to handle non-convex shapes, and the dynamic scenarios highlight the real-time behavior. In summary, we provide an efficient approach to create joint-level distances for any special point to arbitrary joint configurations, and it can be used for planning, control, optimization, and learning. Thanks for listening.
All right. Do you have questions for Yiming?
Thanks, very interesting. Is the definition here of the configuration space distance function dependent that your robot only has rotational degrees of freedom?
I'm sorry?
You only consider rotational joints?
Yes, the configuration space is corresponding to the joint angles of the robot, and here we consider the distance is the L2 norm distance from the current configuration to the configuration that will get contact with the object.
What about robots without rotational degrees of freedom?
Without the articulate, I think it can be the same, but this distance might be not be the angular distance. It might be some other distance definition, I guess.
And you're using a neural network. How much do you lose in accuracy when you generate the compact version of your CDF?
For the neural network, we just use a simple multi-layer perception. And for the data, we voxelize the 3D workspace as a 20 by 20 by 20 volumetric grid.
And you lose accuracy when learning?
Sorry, yes, during learning we will lose some accuracy, but we have a compact and a continuous representation.
Right, do you have another question?
Hello? Yeah, thank you for this very nice talk. Earlier you mentioned something about the icon equation, and if I recall, it's something related to value function of some time optimal control problem. Give us a sense of how closely related your method for computing your CDF is related to something that would, well, solve the icon equation in this case.
Actually, here we didn't solve the icon equation. The idea is that the CDF comes from SDF because SDF is the solution of icon equation. Here we just compute the L2 norm distance by finding the closest one. But the CDF should follow the icon equation. So we put the icon equation at when we train our neural network. So the icon part is a loss constraint to optimize our network.
Oh, so you gather the data from your procedure where you sample from the SDF, and then you use the icon equation as a regularizer when you train.
Yes.
Okay,
yeah.
that's pretty smart. Thank you.
But after the network is trained, the representation should satisfy the icon equation. Yeah.
Okay. Oh, great. Okay. Thank you.
Great. Thank you very much. Next up, we have Bernhard presenting his work on towards tight convex relaxations for contact-rich manipulation.
Okay. Hello, everyone. My name is Bernhard Paes-Krestal, and this is our work on using tight convex relaxations for contact-rich manipulation. So contact is everywhere in robotics, and we're all familiar with these famous examples. But while we have many impressive results, there's still a lot of unsolved problems in this domain. Consider, for instance, a simple example, like this non-prehensive manipulation in the plane task, as used as an example in the recent diffusion policy paper. What this paper showed is that behavior cloning methods works really well for these types of problems. However, scaling these methods can be hard because it relies on having good demonstrations typically provided by humans. So an important question to answer is whether we can provide high-quality data using trajectory optimization methods. So can we actually solve a problem like this using trajectory optimization? So while it's a seemingly simple problem, it highlights some of the key difficulties for current model-based planners. On the one hand, it's a hybrid system, because on a high level, we need to make these discrete decisions about where to make contact. And on a low level, we need to make continuous decisions about what motions to take in each contact mode. In addition to this, the system is under-actuated because the object can only move when pushed. And we also want to stay collision-free when we don't intend to make contact. So why don't we use an existing method to solve this problem? Well, most current methods do one of the following things. They either artificially decouple the discrete and continuous parts, which often yield suboptimal or even low-quality trajectories. Or they blend the discrete and continuous parts, but only in a local fashion, typically around the provided initial guess. Or you can try to which can be unreliable and often fail. Or you can try to resort to global mixed integer methods, which tends to be expensive and scale poorly. So we propose a new method that is based on convex optimization. Our method is global, and it achieves plans a few % away from global optimality. It's reliable, and it always succeeds in finding a feasible plan for all the problem instances that we tried. And it's efficient in the sense that it scales polynomially and not exponentially. So how do we achieve this? Well, the first step is to consider planning in a fixed contact mode. So let's say we know what face of the object we want to make contact with. Already, this is a reasonably hard problem, because it involves planning over rotation matrices, as well as cross products between decision variables such as contact locations and contact forces, which yields bilinear and hence non-convex constraints. However, what we find is that we don't have to solve the non-convex problem. Instead, we can use a tight, convex, semi-definite programming relaxation, which allows us to approximate planning in a fixed mode as a convex program. And this we can use as a building block to solve the overall planning problem. So the next step is to compose these contact modes. And to do so, we will use a recently proposed framework called the graph of convex sets. On a high level, this framework allows us to compose convex programs into a graph structure and solve them simultaneously. And while this is, of course, a computationally hard thing to do, we have a recent line of work which shows that many of the problems that we care about can be solved efficiently through a tight convex relaxation. So we formulate the contact planning problem using GCS as follows. For each of the contact modes in the system, we add a vertex in the graph, which means that by picking a path in the graph, we actually pick a mode sequence for our plan. So the entire contact-rich planning problem can now be solved as a shortest path problem in this graph, which we can do as a convex program followed by a quick rounding step. So now for our results. We compare our method with a state-of-the-art contact implicit trajectory optimization method. And we find that this baseline method works reasonably well for a simple problem instance like this one. But for a harder problem geometry, it only succeeds 1 out of 10 times. And this is because the method is local and struggles to find complex mode sequences that deviate significantly from the provided initial guess. In contrast, our method always succeeds in finding a feasible plan for all of these problem instances. And this is because our method is global and is capable of doing global reasoning without relying on an initial guess. The planning times are between a few seconds to a minute. And in addition to this, because we use convex optimization, we can actually bound how far we are from global optimality, which we find to be empirically around 10%. We're also excited to share some ongoing work. So here you can see some preliminary results where we're trying to train a diffusion policy for this task, but with a reduced amount of data. So here we only use 50 human demonstrations, and 90% of the data or 500 of the demonstrations are planned directly from our method. Thank you so much for listening.
Thank you. Questions?
The demo looks great. So I'm generally curious about how long does it take and what does it take to actually construct the graph of convex sets, and how long does it take to do the planning, the general efficiency of the whole pipeline?
Yeah, so that's a great question. So here for the box-shaped geometry, we plan in between around 7 seconds. And for the more complicated geometry, the T-shaped one, it's like a minute or a minute and a half. So it does definitely scale relatively quickly with the object geometry. Generating the convex sets. So in this case, we assume that we know the geometry of the object. So we can generate the convex sets based on the geometry. We also have a line of work which allows you to algorithmically find kind of these convex sets for you but those are tailored more towards collision-free planning, so we would have to do some more work to adapt those to these types of problems. Thank you.
Hi, I'm over here.
Oh.
Thank you for the great presentation. I think I have a related question. So first I was wondering about the geometry, how you can maybe make it more complex and how you would go about it, but also about maybe not sliding on the plane. What about more free space motions or problems in SA3 space? How would you go and scale that?
I see. I mean, our method can certainly handle sliding modes. And were your question about three-dimensional systems? Sorry. Okay.
Yeah.
So we have done some preliminary experiments with three-dimensional systems. While in principle, our method should be able to handle those cases as well, we are limited in kind of the size of the problems that we can solve currently because we are relying on explicitly enumerating all the contact nodes in this graph. But we are currently working on relaxing that assumption and kind of get around this having to explicitly enumerate contact nodes, which I think would also allow us to scale to much more complicated problems.
Thank you.
Great, thank you very much.
Our next speakers are Ishika and Yafei, and they will be presenting the Colosseum, a benchmark for evaluating generalization for robotic manipulation.
Hello, everyone. Today, we'll be presenting on our work, the Colosseum, a benchmark for evaluating generalization for robotic manipulation. With traditional imitation learning for robotic manipulation, human demonstrations are often collected in specific environments to train policies. However, this policy typically only performs well in similar environment, and that does not reflect the demands for real-world deployment. A generalist robot should be able to adapt to variations in object color, size, texture, and even camera pose. Quantifying generalization is critical for measuring the progress in multitask robotic transformers, and we need a robust framework to test this at scale, ensuring that they reflect all real-world conditions. So the question is, how can we effectively evaluate manipulation policy in a realistic scenario and eventually developing a unique test for generalization in robotic manipulation? So perhaps the answer will be a benchmark. Benchmark in computer vision has significantly advanced the development of more generalizable vision systems over the past decade through numerous competitions and challenges. Breakthroughs in AI has also often landmarked by such benchmark, for example, ImageNet and WALS. Therefore, we believe a unified benchmark for evaluating generalization in robotic manipulation can help us to actually drive the field forward. In the past, there has been several benchmarks that tries to do this. However, several factors are often overlooked. This includes task categorization, scoping of evaluation, reproducibility, and the diversity of the models that's being evaluated. So to address this, we introduced the Colosseum, built upon our bench. It aims to provide a wide range of practical tasks and includes an automated pipeline that's capable of generating up to 14 perturbation factors that can affect object appearance, geometrical scale, and environmental conditions systematically. We define perturbation factor as a formulation of sim property. This perturbation factor can be altered to cause a distribution shift from its training data during test time. We define 4 categories of perturbation factors: manipulation object perturbation, receiver object perturbations, background perturbations, and physical perturbations. We propose Colosseum as a challenge to foster the development of generalizable behavior cloning models. The challenge consists of 4 key components. Participants first generate a standard training set for over 20 tasks without perturbation factors. Participants then train their behavior cloning model using our standardized data set. And lastly, the models are then evaluated across all 14 perturbations in Colosseum, and we will rank the models on leaderboard based on their percentage change for the performance over these perturbation factors.
In our analysis, we study 5 state-of-the-art baselines established as strong robot learning methods and diverse in their approach. In our 2D learning baselines, we include R3M and MVP-based models that use visual encoders pre-trained on out-of-domain task-agnostic real-world images. In our 3D learning baselines, we include PERACT and RVT that are transformer-based robotic manipulation methods. They use tokenized voxel grid or re-rendered multi-view images to input to produce translation key points as individual voxel or a heat map over the images. Lastly, our zero-shot manipulation from large pre-trained model baseline include box poser, a framework that extracts affordances and constraints using LLMs into 3D value maps. Our investigation finds that both 2D and 3D models are affected by color-related perturbations and especially distractors. 3D models that do not directly learn on specific views are robust to camera poses. 3D models outperform 2D models in general. Zero-shot models cannot solve many tasks but are invariant to environment perturbations. Here we present a few failure cases. In the presence of distractors, the robot goes for the distractor instead of the ball. When the drawer is smaller than that seen in training, the robot predicts the grasp incorrectly. Under an unseen lighting condition, the robot doesn't move due to shift in the input space. For an unseen colored spatula, the robot fails to pick it up. In our real robot experiments, we mirror 4 RL bench tasks in real world along with their perturbations via 3D printing. Here we present demos for the individual setups of tasks and perturbations in the real world. Our real-world result presents training and evaluation of the Parak model in simulation and mirrored real-world setup. The R-square values on the right indicate a strong alignment between evaluation done in the Colosseum in simulation and in the real world. To conclude, we propose the Colosseum, a novel manipulation task benchmark that systematically perturbs the training environments along 14 perturbation factors. The Colosseum Challenge and Leaderboard will provide us a unified platform to develop, evaluate, and compare future robotic manipulation methods that stand the test of robustness and generalization. Thank you, and please visit our poster if you're interested in using this benchmark.
Questions? Over there.
Hi, great talk. Yeah, really cool initiative. I was curious about the philosophy. It looked like from your figure that you want to train without perturbations and then test with perturbations. And what's the thinking there?
So the idea is like when you are trying to train a model like to open drawer, it should be able to open the drawer regardless of like any changes in the scene, because the act of opening the drawer is still the same. Just like if it looks different, it should still like able to execute the skill. So we try to like add these perturbations like as unit tests in each like factors, in each direction of the factors, to test like individual perturbation factors that could like affect the performance of the model.
Why not train with some perturbations?
I think it's like probably because you might not be able to obtain those perturbations. So it's similar like when we rehearse for this presentation, we are not able to stand on this stage and rehearse it. Yeah.
Great, cool, thanks.
Are there any other questions? Up there.
Hi, very nice talk and nice paper. Maybe following up on the previous question, why don't you consider maybe distributional shifts in the perturbations? So I have like allow to train models with some perturbations, but then actually change the frequency or distribution of them.
So you mean that like have some perturbations in the training set and then change?
Yes.
And then so the data distribution shift is like smaller than like for example like you train on some color changes and then you test on like different color changes. Yeah, I think like some kinds of augmentations could help. Just that like the idea is that we don't want to like demonstrate on the same color of the object as we are testing on. We wanted to like really generalize to like unseen setups. But I think like having some kind of augmentations, of these kind of augmentations and like domain randomization might help.
I think also in our paper, if you take a look, we actually train with all variations, and we show that the upper bound is not as good as training with, like for those cases when you test in no perturbations. So we actually sort of establish an upper bound in this case.
Great, thank you so much.
Great, thank you very much. Next up, we have one-shot imitation learning with invariance matching for robotic manipulation presented by Xinyu, who is not here. Huh? It's just video? But where's the presenter? It's just, they're just going to play the video? Yeah. Can you guys turn on the sound? No, we have no sound. Okay, for the sake of giving them a moment to try to figure this out, well, maybe you can move to the next one.
The next one is Miguel, that is presenting tactile-driven non-prehensile object manipulation via extrinsic contact mode control.
Does this work? Okay, cool. Hi, good morning. We present our work, tactile-driven non-prehensile object manipulation via extrinsic contact mode control. In this, this is going so fast. We consider the problem of tracking a desired object trajectory under rigid body dynamics. Our goal is to optimize a sequence of end effector poses that result into desired extrinsic object poses, contact modes, and transmitted ranges through a grasp object. Our method considers the tactile sensor compliance and the contact mechanics. So we use tactile sensing to estimate the grasp object pose, extrinsic contact location on the grasp object, and extrinsic object pose. We use April tags exclusively for evaluation and for obtaining the initial extrinsic object pose. Here we show an overview of our method. We formulate our method as gradient-based trajectory optimization, where given a set of desired extrinsic object trajectory and contact modes, our goal is to optimize a sequence of end effector poses and grasp object poses that obey the sensor compliance and the contact mechanics. The first model that we'll consider is the tactile sensor compliance model, which characterizes the force deformation relationship of the tactile sensors. In general, our approach can use any differentiable characterization of the tactile sensor compliance. However, we model this relationship as transmitted ranges are linear with the grasp object displacement, as shown successfully in previous approaches. Next, given the object poses, we can formulate the contact Jacobians and use them along the computed external range, contact mode, and parameters to compute the contact forces. To compute these forces, we solve the following optimization program, which imposes extrinsic object range balance, grasp object range balance, and contact constraints following Coulomb's friction. Note that given the Jacobians and the contact modes, this takes the form as a quadratic program. Finally, given the computed forces and the object poses, we can formulate a differentiable loss function that can impose robustness, smoothness, target contact forces, and avoid penetration. Then we can backpropagate this loss around the different differentiable modules to iteratively optimize the end effector poses and the grasp object poses. Next, we'll see some of our experiments. We test our approach for prehensile object manipulation for different skills. Here we show on the left-hand side object pivoting about the corner, and on the right-hand side, object sliding around the corner. We also test our approach for non-prehensile object manipulation for 4 different skills. Here, from left to right, we show object relative slip, extrinsic object pushing, and object relative pivoting. Here we compare the optimized trajectory shown on the left-hand side to the actual executed trajectory shown on the right-hand side for the last of the 4 non-prehensile skills. We test our approach for a diverse set of object geometries. Our approach considers object geometries to be polygonal. We further test the robustness of our approach against external perturbations. Finally, we benchmark our approach against sample-based trajectory optimization methods like MPPI or improved cross-entropy methods. Compared to these baselines, our approach obtains smoother trajectories requiring less samples. We further tested our approach for a more rigid tactile sensor, like the Gel Slim. If you have any questions, please visit our poster. Thank you.
Do we have questions for Miguel? Yeah, one over there.
No, it was super interesting. I was just thinking about if you, like you obviously had a force sensor at the wrist as well.
Yes.
And I was just wondering how much information you're getting from that compared to the tactile pads, and if you'd be better off using both, or there's some complementary information, or if there's completely redundant.
So it's a question, how much information does the torque sensor obtain compared to tactile?
Yeah.
Okay, yeah. So the force sensor on the wrist is mostly used for like evaluation and like obtaining ground truth force estimation. We obtain forces through the tactile sensor deformation. Yeah.
But like, could you do the same thing with just the force sensor and a similar approach?
Yeah, I mean, as long as you have a way to measure forces, yeah. And model the compliance of some element.
Okay.
There is another question over there.
Thank you for the talk. I really like that you used multiple different, really different tactile sensors in your work and experimented with them. But I'm wondering about if you looked at how finicky is the tuning of the model that you're using to match basically the characteristics of these sensors?
That's a good question, thank you. So for across the sensors, we follow the same compliance model. We just tune them like to model the different compliance. One is way more rigid. It's in fact up to 5 times more rigid than the soft bubbles, the tactile gel film, but both were for the same model is applied to both sensors. I would say that something that we observe is the higher the compliance, maybe we have more better tracking of the desired forces. But yeah, or the approach is applied the same for both.
And was it hard to find the right hyperparameters of the model?
Let's say that we use the linear characterization, so we just had to collect a few trajectories with the object grasp, and yeah, fit some regression. So it was, I think, quite simple.
It's mostly about sensitivity. How sensitive was it
Oh,
to that regression?
that question was sensitivity?
Yeah.
Oh, I didn't hear that, sorry. Sensitivity.
Basically, how much can you be off with your model parameters from how the sensor actually works, basically?
Yeah, this is something that we haven't evaluated numerically, but one of the limitations I would say that we assume that the grasp object is sticking on the grasp. So it starts slipping. This is something that it's not accounted. So if we have evaluated our approach for like open loop, and this is one of the failure cases. With closed loop, we kind of can recover this, but yeah, that's one of the. We are sensible to this.
Thank you.
Thank you.
Great, thank you. All right, I'd like to thank all of our speakers. Great job. Thank you everyone for coming. And we have a small change in the program to the conference. The awards session will be at 11 now, and the poster for imitation learning will be at 11:30, the same places as they were before. Thanks a lot, and enjoy the coffee break. Yay.
Hello everyone. So this is the last session of this RSS conference this year, and yeah, we don't have much time. Much people, but it was a start. So the first paper is Droid, a large-scale in-the-wild robot manipulation dataset, presented by Alexander from Stanford. Yeah, please take it away.
Okay, so I'm gonna disappear. Wait, there's sound, right? Yeah.
Hi there. My name is Alexander Kazatsky, and for the last 2 years, I've been working with nearly 100 collaborators to address what we feel is one of the biggest bottlenecks in robotics today. While other subfields of deep learning have been excelling due to the prevalence of large data sets, robotics has been left in the dust. Existing data sets simply lack the required diversity that neural networks need in order to generalize to novel situations. We set out to put a serious dent in that issue. And so, without further ado, I'd like to introduce the Distributed Robot Interaction Dataset, or DROID for short. Thank you very much. Welcome to the future. Oh my god! It's robot. Why are we still using hot coffee? DROID is the most diverse robotic interaction dataset ever released. It includes 65,000 teleoperated trajectories of robots performing general purpose skills in real-world homes, just like this one. Just how diverse is DROID? Well, DROID includes 86 tasks, 564 scenes, and 52 buildings. Spread all over the world. And remember, most of our data collectors are robot researchers themselves, meaning that you can rest assured that each trajectory is collected with every possible ounce of attention to detail. And of course, we live with safety every step of the way. Before I leave you all, I'd like to take a moment to thank my incredible collaborators. This dataset wouldn't have been possible without the passionate volunteering that each and every one of them put into this project.
Hey, Mohan, how you doing? How's the data collection coming along?
Sasha, I know you want us to give 8 hours of data every day, but this is getting ridiculous. My wrists are really hurting. I'm probably going to visit the doctor soon.
Really? Well, I imagine your voice really hurts with all that complaining too.
And to the rest of you out there, I hope that you have just as much fun using the DROID dataset as we had collecting it.
She said she was so funny, and I don't think she's really that funny. I mean, it's one thing to be funny, but it's another thing to post like a...
Insert smooth transition. Okay, so now that we've had some fun, I'm on a timer, so now that we've had some fun, let's go over some concrete information about the DROID dataset, which was a collaboration between 13 international institutions. Hard finding a meeting time. It includes 76,000 teleoperated trajectories, 90K if you include failures. It has 564 scenes from complex real-world environments spanning 52 buildings and behavioral diversity from 86 tasks, household tasks. It has unprecedented diversity in scenes, tasks, and viewpoints. Breath. It also has rich annotation data ranging from calibrated multi-view cameras, stereo video that enables depth, and language annotations. And everything is fully open source and readily available, from the dataset itself to the robot hardware to the policy learning code. But don't take my word on it. Check out the dataset for yourself using our interactive dataset browser, which is available on our website. And unlike me, it's not just pretty to look at, it's also useful. Co-training with DROID yields not only improvements in in-distribution performance, but also strong out-of-distribution generalization across a diverse suite of tasks. Since its release, we've seen people studying how DROID enables pre-training capabilities in everything from household tasks to automating wet labs, advanced observation spaces, viewpoint generalization, as well as those simply benefiting from a more robust experiment setup, thoroughly tested control stacks, and the visualization tools that come with our framework. And if you're not using DROID already, you can turn your life around with 10, count them, 10 lines of code. And before I leave you all for real this time, I'd like to say one more thank you to the nearly 100 collaborators that were involved in this project. This data set wouldn't have been possible without a lot of people working very hard towards a common goal, and I'm extremely grateful to and proud of all of them. And with that, I give you the distributed robot interaction data set, downloadable today.
All right, happy to take questions.
I'm nervous. What may I answer? Don't be shy. I'm missing. Oh, hi. Not for me.
Hi, thanks, amazing work.
Thank you.
I keep on hearing that there's some issues with calibration of that data. Is that a plan to fix this? Because I assume it could be fixed or something like that?
Yeah, the calibration was done by data collectors. There's some mistakes in there. TRI is doing some lovely work. We're releasing it probably within a couple weeks. Something where it basically confirms which of the scenes are correctly calibrated and which are not, as well as does some multi-view alignment. So that should be resolved. So
exactly. So there was a question exactly, maybe it's possible to realign them even post-effect, right?
Yeah, there's some information in there which helps.
More questions from audience? Yes.
I think there's a nice catch.
Hey, hi, Sasha. Sorry, yeah. I'm wondering now, hindsight, what would you do differently if you had to recollect the data set? What are kind of the lessons learned, basically?
I think the main thing was that onboarding of new people was really hard, and the quality in the beginning is lower because people are learning. I think that the best and the fastest quantities of data were produced by people who already had experience. And so I think there's a huge benefit to working with a smaller team of data collectors that really know what they're doing versus onboarding like as many people as possible. You get more diversity, and maybe at some point that'll be good, like diversity and quality. But I think for the stage where things at high quality is best.
Thanks.
All right, let's thank the speaker again. The next paper is Multimodal Diffusion Transformer, Learning Versatile Behavior from Multimodal Goals, presented by Moritz. Please take it away.
Hey folks, I'm Moritz from the Intuitive Robots Lab, and I'm excited to present our work on learning better policies from partially labeled datasets. So this year at RSS, we have seen tremendous success of scaling imitation learning towards more versatile agents using language conditioning in the real world. And the two key ingredients for this success have been the availability of nice large-scale datasets, such as Droid, together with the availability of expressive and scalable policies, such as ACT or diffusion policies. Those two have led to versatile policies that can solve a wide range of tasks using language conditioning in the real world. But most of the large-scale datasets, especially the older ones, are only partially labeled or not labeled at all. So this raises the question of how we can make better use of partially labeled datasets for training better language-conditioned policies for real-world behavior. To this end, we introduce Multimodal Diffusion Transformer, or short for MDT, which combines an updated transformer diffusion policy together with two self-supervised objectives that are only learned end-to-end to enhance the understanding of goals formulated in either language or vision, which allows us to make better use of partially labeled datasets, but also increase the performance across many language-conditioned benchmarks in simulation and the real world. While self-supervised learning has been used a lot in robotics in the last few years, the main focus has been mostly to learning better individual modalities, such as CLIP learning multimodal goal space, or something like Voltron that learns powerful image feature encodings. However, the most important feature space are not the individual modalities, since our policy combines all of these different inputs into its latent space. Prior work usually then just freezes all of their pre-trained embedding models and trains the model using the action learning phase. However, we raised the question, why stop there? Like, the most important feature space is the latent space of our policy, and we should focus our alignment there and not of the individual modalities. To do so, in MDT, we include 2 additional auxiliary objectives during the action learning phase, which makes our training efficient and fast. And the first one is called contrastive latent alignment, which is a clip loss, which tries to improve the policy's understanding of multimodal goals. We therefore take during training randomly sample future images as our goal image, and if available, take the same goal expressed as language. Then we enforce the latent space of our policy of the same state with different goals to be close together, while other goals and other images are pushed away. This enhances the policy's understanding to better align goals formulated either as language or image, while we can make use of all the good pre-trained models like LIV or CLIP, but now we take the full state context into account, which makes it easier for the policy to understand the different modalities. Together with CLA, we also use an auxiliary objective called mask generative foresight, which is a simple reconstruction loss that enforces the policy with some auxiliary network to reconstruct missing patches of future images. This enforces that the same goals specified in different modalities should lead to the same behavior and increases the spatial awareness of the policy. Using these 2 losses, we evaluate MDT across more than 150 tasks in simulation and real world with datasets that have as little as 2% language annotations. Some results I want to highlight: our performance on Kelvin, where we achieve a new state-of-the-art performance while training 10 times faster, being the fastest to roll out, and also outperforming all methods. We also show that MDT without auxiliary objectives, shown in blue, has a lower performance than using our 2 objectives together. Also, in just 1 denoising step, we achieve really good performance with diffusion. And the same results are also shown in the real world, where both auxiliary objective enhance the learning from the partially labeled datasets, and we surpass prior strong methods such as ACT by learning from 4 hours of uncorrelated play data. So to summarize, don't throw away your self-supervised objectives, because they could be really helpful to enhance your policy. Thank you.
Questions from audience? Yeah, I have one question. So in your research, it's really great, but I also see that MDT minus this auxiliary losses also work pretty well.
Yeah.
So then, like, what's the main, main component that makes it work a lot better than the prior state of the art in that sense?
So architecture-wise, I optimized the diffusion. So the original diffusion transformer policy had some improvements that we're able to make. So by switching, so adding the encoder and using this film conditioning for the noise in the decoder is able to make the noising a lot better and increase its performance there. So architecture-wise, that made some differences already.
Got it. For that, did you use the data that doesn't have a language annotation?
Yes, so everything was trained in this setting on the full data set to show how the 2 objectives can help to make better use of the unlabeled part.
Great, thank you. Questions from the audience? No? Let's thank the speaker.
Thanks.
All right, the next paper is Don't Start from Scratch, Behavioral Refinement via Interpolate-Based Policy Diffusion, presented by Kai-Chi. Please take it away.
Okay, hi everyone. My name is Kai-Chi from National University of Singapore. Today I'm going to present our work, Interpolate-Based Policy Diffusion, that generate actions from more informative source rather than a standard Gaussian distribution. Our method enables fast inference and require less training data. Recently, diffusion model has been used as a powerful policy representation for imitation learning. Since these methods are good at modeling multimodal distributions and generating high-dimensional, long-horizon action sequences. However, to achieve better performance, these models typically require more diffusion steps, leading to increased inference time. This brings us to the key question we aim to answer in this paper. Can we achieve better performance cost trade-off? Why it is challenging? In common diffusion models like DDPM or DDIM, we start by adding noise to the original data until it reaches a standard Gaussian distribution. Then we learn a reverse process that iteratively generates actions from this standard Gaussian. However, the key problem is that this standard Gaussian distribution could be quite different from the human demonstrated behaviors. As a result, the diffusion models need more diffusion steps. How to solve this problem? Our key insight is that instead of starting from a random Gaussian distribution, we can start from a more informative source. For example, in our common robotics tasks, we can define a heuristic rules as a source. We can train a simple model on the domain data. We can adapt models from similar tasks, or we can use foundation models. However, we cannot directly employ the common diffusion model like DDPM over here, since we need to design specific Markovian forward process to reach our customized source policy. This is typically infeasible if our source policy is more complicated than a standard Gaussian distribution. So over here, instead, we employ a bridge diffusion model called stochastic entabulance that can bridge two distributions. Intuitively, stochastic entabulance entabulates between the source and the target. For example, we can use a linear entabulation, but other kind of entabulant functions can be used as long as they satisfy certain boundary constraints. We call our framework bridger. Training this model only involves learning velocity fields by minimizing simple regression loss. In our experiment, we find better source policy typically results in a better final policy. In our grasp generation tasks, we initialize our grasp samples near the object and towards the centroid. We find this kind of simple heuristics could significantly improve the task performance compared to the baseline diffusion method that starts from random Gaussian. We also provide a theoretical analysis in our paper. In our real robot experiment, we find the baseline diffusion method often fails when the number of diffusion steps is limited to 5 because it denoys the actions from a very uninformative Gaussian distribution. In contrast, our method, starting from better source policy, could achieve higher success rate. We also tested our method on a wound cleaning task, which involved grasping a sponge to clean a marker on a synthetic human tissue. This task is challenging due to the multimodal demonstrated behaviors and the high-dimensional action space involved. The baseline diffusion method, like DDIM, generates noisy action sequences. This makes tasks unsafe and prone to failure. In contrast, our method, starting from better source policy, generates smooth action sequences, leading to this kind of successful task completion. In conclusion, we present Bridger, an entabulant-based policy diffusion from more informative source. We find that better source policy typically yields better final policy and can achieve better performance cost trade-off. For more details, please come to our poster session later. Thank you.
All right, questions from the audience? Yes, over there.
You hinted during your presentation that there are some constraints for the stochastic interpolants to be able to bridge the two distributions. Can you expand on that?
Yes, so I can give you a high-level idea of this, but if you want to know more mathematical details, we can discuss in our poster session. So basically, you need to ensure that if you interpolate between this source and the target, you need to say, let's say you start from t equals to 0 to t equals to 1. So you need to make sure that when t equals to 0, your interpolation should be the same as the source policy. And when t equals to 1, your interpolation should be the same as the target policy. So that's basically the high level of this constraint. Yeah, but if you want to know more mathematical details, we can discuss it.
There is one more question over there.
Really cool idea. Yeah, actually, I'm super excited about this. One question I had is if you still have a way to jump from like to any intermediate diffusion step during training. Like, can you jump from t equals 0 to t equals I, or you have to go through each step 1, 2, 3, 4 up to I?
So basically, I think this is a hyperparameter of the solver of this kind of stochastic differential equation. So basically, over here, we just discretize the times from 0 to 1. If you want to diffuse less steps, then, for example, if you want to diffuse like 2 steps, you just discretize this space to 2 parts, and then you do this kind of jump. But if you want to do more diffusion steps, then you should discretize to, more spins over there, and then you need to jump more steps.
All right, sir, I'll follow up in the poster. Thanks.
All right, please thank the speaker again. All right. Gia is presenting learning manipulation by predicting interaction.
Hello, everyone. My name is Jia Zheng. I come from Shanghai AI Lab. I'm glad to present our paper, Learning Manipulation by Predicting Interaction. In the field of visual motor control, a number of approaches find that pre-trained representation enable more efficient robot learning. However, in domain robot data is scarce. In response to such issue, many researchers explore to leverage large-scale human video demonstration. We summarize the roadmap for such methods. The representatives are R3M, MVP, and Watron, and we propose MPI method at this conference. MPI is an interaction-oriented representation framework towards robotic manipulation. Unlike prior work grounded in contrast-free learning like R3M, masked signal modeling like MVP, or video prediction using sequential frames, MPI takes the key frame as input and instructs the model to both predict the transition image frame and detect the manipulated objects. With MPI, we enhance the pre-train process to acquire more informative representation, thereby leading to a clear improvement across various downstream tasks. This is a pipeline of MPI. We take equal 40 hand and object subset as our pre-trained dataset. During pre-train, one initial frame, final frame, as long as language instruction are fitted into our network. And they go through a multimodal transformer encoder and transformer decoder. The decoder comprises a prediction transformer and a detection transformer. The prediction transformer is designed for predicting the transition image frame, and the detection transformer is designed for inference the object or inference the location of the manipulated object. And we also realize the bidirectional information interaction between these two modules. And in the downstream task adaptation, we designed these two scenarios to evaluate the effectiveness of different pre-trained encoder. And in the complex kitchen environment, we have these 5 tasks. And in the clean background environment, we designed the 10 manipulation tasks. And for each task, we collect only 10 demonstrations. Firstly, let's look into the examples in the complex kitchen environment. The task involves such as lift up the pot lid, take the spectrum of the shelf, etc. And we also conduct real-world generalization, real-world validation on generalization. First, look into the generalization on object variation. The task involves lift up the pot lid, and where we substitute the white pot with a wooden one. And here is the performance of one of our baseline model, R3M, and our proposed MPI. And also, let's look into the generalization on background distraction. We regard the task of put a banana into a jar, and we introduce background distraction by replacing the daisies with roses. And here is the performance of R3M and our proposed MPI. And we are going to briefly present some examples in the clean background. This task involves some basic manipulation skills, such as pick and place or articulated object manipulation. And we also extend our evaluation to simulation environments, such as Frank Kitchen, Metal World, and reference expression grounding task. And the result revealed that the MPI acquires more generalizable representation than other methods. To sum up, MPI instructs the model towards predicting the transition frame and detecting the manipulated object, thereby fostering a better understanding about how to interact and where to interact. The limitation of MPI mainly lies in the requirements of the explicit annotation, but such problem can be alleviated by the introduction of well-established auto-labeling tools. And the codes of MPI are released. Welcome to have a try. That's all of my presentation. Thanks for your attention.
Any questions from the audience? Yeah, I can ask one question. So, yeah, for the keyframe learning, how did you extract the keyframe, and how important to get the intermediate, like a keyframe, to predict?
Firstly, the keyframe is annotated in the Eagle 4D handled object subset, and it's provided by the original dataset. And the key mechanism of our pipeline is to produce the transition frame with the input of initial frame and the final frame.
All right, thank you. Any question from the audience? All right, then we can move on to the next paper. Thank you. Thank the presenter again.
Okay, next we have URDeformer, a pipeline for constructing articulated simulation environments from real-world images, and presenting is Dieter.
Yeah, hi, thanks a lot. Yeah, I'm presenting URDeformer on behalf of Zoe Chen. So this is work done by Zoe and collaborators and co-advised by Abhishek Gupta and me, mostly at the University of Washington. We've seen many examples that training and simulation, of course, has the advantage that you can do it very fast in a scalable way and also safely. One of the key questions in this context is really, how can we generate the environments in which we train these robots in an automated way? So we see here many examples, but most of them are actually manually designed, and that is still a very significant effort. So the goal of URDeformer is to scale this up by coming up with an automatic data generation and environment generation procedure, which just takes in a real-world image, such as here of a kitchen, and then automatically transforms it into a UDF description here on the right that we can then use to train a robot and evaluate a robot in. The overview of the URDeformer is where the input is first an image of the scene. We feed that into a detector. The detector detects certain parts in the scene, like handles, doors, drawers, and cabinets. Then we feed this into a vision transformer that gives us features that we can feed into the next transformer that generates for all the different parts, generates outputs that describe these different parts with respect to what kind of part it is, how it is connected to other parts in the structure, and also the position of the part, bounding box information. We can then combine all this into information to generate a UDF description of this object, and finally get then the 3D description of the object itself, all just driven by an image. Of course, the key question in this context is, where are we going to get the training data from to train this model on? Because we need images paired with 3D URDF assets. And there was no data set like that out there, so we had to generate it. And the trick is We start out with URDFs, and the idea is that it's relatively easy to generate URDFs in a templated way for certain cabinets and layouts and things like that. For each of these URDFs, we can then generate meshes and a really simplistic kind of simulation asset, as you can see here. We can then render images on them that look very unrealistic, as you can see here. And then we use actually stable diffusion, a specialized form of that, to generate images that look very realistic and that are consistent with the structure of these objects. And now we have a data set of URDFs paired with images that look realistic, and we can train the URD former to invert this process, meaning going from the image back to the URDF. And once the URD former is trained, we can then deploy it where the input are just images of these objects, and it's going to generate URDF descriptions of them. Here's a bit more information on this first data set generation that we use to train the system then on. Here you can see rendered views on different kind of assets that we generate with the URDFs automatically. The key trick is that we need to use a masking process to get stable diffusion to generate images like these that are consistent actually with the structure of the objects, which means the handle have to be at the right locations, it has to have the right kind of drawers and things like that. And you can see here that that actually works very nicely. More details, of course, in the poster. Here's an outcome of this data set, for instance, in the upper row then. Once we train the URD former, it works as follows. The upper row is the input to the system. Next is we use grounding dyno that we fine-tune to detect parts of these objects, and outcome then, based on the URD structure that the URD former generates, we can generate these assets then. It doesn't only work for individual cabinets, we can also do it for full kitchen scenes in a hierarchical fashion, and also for appliances like fridges and microwaves, and also, for example, swivel chairs and things like that. It's not perfect, obviously, so here are just some examples for where it fails. And typically we see failures when the structure is very complex, when the view onto the assets is very tilted, and things like that. So I'll encourage you to come to the poster to see more information. We also then show that this can be used in a real robot deployment, where we put a robot in front of one of these cabinets, we take an image of the cabinet, feed it through a URD format to generate a digital twin of it, and then we can train a robot policy in the digital twin with the appropriate kind of randomization, and we show that this can then actually go back to the real one, and the robot can execute the trained policies in the real world. So we have this real to sim to real loop working with this URD former as well. There's website code is available. There's also a nice GUI if you want to improve on the kind of bounding box generation that the system requires. Happy to take questions.
Any questions? You have someone? Oh, Roberto, there. Ah, no, okay.
Hi. Yeah, great talk. Really cool idea. I was curious, I guess what you're presenting overall is kind of a real to sim to real pipeline. And I'm wondering if you really think you need that as opposed to just training in sim over diverse cabinets and then going to real.
Yeah. So there's two uses for this URD former framework, right? One use case is just to generate a large data set of very diverse randomized assets, and you could use that to train. We haven't really investigated that training pipeline yet on using it. So here we show that is kind of a second use case, right, where you can use it for this digital twinning. And what we show in the experiments is that actually using this digital twin that you get from the URD former, and then do some randomization, because it's obviously not perfect, do some randomization on the scales and things like that, works better than just using fully randomized assets to train it on, right? Because you're just more targeted to the object on which the robot then operates, rather than this purely random training.
Okay, I think there was a question over there.
Hi, hey, Dieter here. You were talking mostly about kinematics. What about dynamics, friction, weight, other properties? I missed that are very important when you want to actually interact.
We haven't addressed that in this case yet. So we're using standard values for those. So on the one hand side, I can imagine for cabinets and things like that, you could come up with, let's say, standard set of values that you could randomize over. But I think ultimately what would be really interesting is that the visual appearance actually provides you quite some information about those physical properties as well. And it would be really cool to see if we could learn those as well, right? But we haven't done that.
Got it. Thanks.
We have time for one more quick question over there.
Yeah. Would it also be possible to obtain some level of uncertainty about what parts of the simulation you're certain about and what parts not?
Yeah, that's a great question. We haven't really looked at that in this context. The one problem, for example, is if we use a fine-tuned version of grounding dyno to get this part detection, and of course there is some uncertainty if the parts are wrongly detected or things like that, right? Then the next step of the pipeline also kind of fails. And taking that into account, where you might have different detectors that you feed into the transformer so that you can sample your DFs out of it, I think that would be really exciting to look into, but we haven't done that yet.
Okay, thank you. Let's thank the speaker again. Next, we have Learning to Learn Faster from Human Feedback with Language Model Predictive Control by Jackie.
Hi, everyone. My name is Jackie. I'm here to present Learning to Learn Faster from Human Feedback with Language Model Predictive Control. And this is joint work with many, many amazing collaborators from Google DeepMind. We know that large language models with in-context learning can enable robots to quickly adapt behavior according to human instructions and human feedback. And this typically takes the form of using an LLM to map human natural language to robot code. And what's nice about this is even if the code was incorrect in the beginning, the humans can provide additional feedback where the language model can revise the code either for correctness or for preference. So in our work, we asked the question, can we improve this teachability of large language models so they can remember the type of feedback that the human was giving and also learn faster and more accurately from human feedback in the future. This is an example of what such a teaching session might look like. So for example, if we want the robot to do this high five pose, we can tell the language model to write the corresponding code. And maybe in the beginning, the pose isn't quite correct. Maybe the paw is not at the right height, or the tilt of the body is sort of incorrect. Through a few rounds of feedback sessions or chat turns, the language model can revise this code and to actually output the correct behavior for a robot task. So imagine if we had a data set of such interactions. Can we take this data set to actually fine-tune and improve our language model? So on subsequent tasks that are both in distribution as well as out of distribution, the language model can write better code and better listen to human feedback. So how do we actually do this? How do we take this data and improve the language model? In our work, we propose language model predictive control, which is a method for both training the language model as well as doing inference with the language model. So during training, the input to the language model is it's a partial chat session, so all the chat turns that the language model has seen so far. And the output is the entire remaining chat dialogue. So it's not just predicting the end correct code, it is predicting the sort of subsequent turns. So predicting the next code output and how the human would react to that and the subsequent code output that follows. And what this does is teaching the language model to model human-robot interactions. And during inference, what we do is we can sample many successful dialogue rollouts from this model that we just learned. And we'll pick the shortest sample dialogue and return the first response from that. So this is very similar or very analogous to doing model predictive control, except the model here is trying to predict how the human would react to the robot behavior that the model was predicting. And we do quite a few experiments on this method across many different tasks and many different embodiments. And then we're mostly looking at this idea of teachabilities, which is the task success rate obtained by the model given a particular number of chat turns. And we see our method, which is in the solid blue line, dramatically improves code writing performance for robot tasks over the gray line, which is our baseline. And what's really nice about this is that not only we improve upon the training tasks, but we also improve upon test tasks, those tasks that the model has not seen before during training. Here's a quick example of the revised robot behavior before and after fine-tuning. So the task here is open the drawer halfway. And in the beginning, the model doesn't quite understand, in order to reach the drawer, it needs to command the robot to move the robot gripper closer to the drawer. And even if it does that, it may not really understand the semantics of halfway. It might open the drawer completely. And through the multiple chat turns, maybe the model is able to eventually get this right. But after fine-tuning, the model is able to do this task maybe with 1 or 2 rounds of chat sessions much faster than before. And I just want to note that this is an example of a test task that the model has not seen during training. And not only does our method generalize to test tasks, it also generalizes to test embodiments, right? So the model isn't just memorizing a set of robot APIs. We see dramatic improvements in performance to new robot APIs, new robot embodiments, doing by-arm manipulation, dexterous manipulation that we have not seen during training data. And lastly, we'll also highlight that this method generalizes to real robots as well. So here the task is pick up the left cold can without knocking over the other one. Before teaching, it doesn't quite understand the sort of collision avoidance behavior that's desired, and after fine-tuning is able to do the task. Our key takeaways here is that we can improve the in-context teachability of language models if we train them to model human responses. In our paper, we discuss a lot more details about what actually makes this fine-tuning work, so including conditioning responses on the style of top users, doing a bunch of data augmentation, and only training our model on successful sessions. If you have questions or just curious about how we improve language models for robotics, please come check out our poster. Thank you.
Hey, questions?
Sorry, very interesting. I'd like to ask you, I've seen the human said at one moment, do it the other way. How this is managed by the robot, the other way, because it depends on the task, it depends on so many things.
Sorry,
he said at one moment in the text, the human says to the robot, do it the other way.
Yeah.
It was for posture,
yes.
But it could be used for any other situation. So how this is managed in your system?
I see. So it depends on the context. The context here being the previous language instructions and the code responses that I've seen in context. So like the input to the large language model is the entire chat history. So in the beginning, the human tells it the actual task, and then it observes the robot code, and then gives a bunch of feedback. So do it the other way is in context of all the chat history. So that's how it makes sense of that.
Do we have more questions? Yep. Harold?
Hi, thank you. It's a very cool talk. I have a question regarding the data scale that you need for fine-tuning this large language model, because collecting this interaction data might not be an easy task as well. So how much data do you need to fine-tune this?
Yeah, so the final models here were fine-tuned on hundreds of chat sessions. So I think if you have a pipeline that can collect high-quality data, this is actually not that much of an issue. I think for us, because we were doing so many ablations and training on different variations, just testing different ideas, we did need a much larger scale data collection effort. So it may be like thousands, more than 10,000 chat sessions to run all these ablations. But once you know what you're doing, you don't have to run all those ablations and just collect the data you want to collect.
But is this data only for single tasks or similar tasks, or you have just 100 sessions and then you can generalize the different modality, different embodiments and different tasks?
Yeah, we collect the data across, I think, 70-something tasks, but we are able to generalize to new robot embodiments, or basically robot APIs, and new tasks that the model hasn't seen before.
Okay, cool. Thank you.
Okay, yeah, okay, we're gonna have one quick question still, if you want. Okay. So can we get a mic over here, please?
Thank you. I was curious about the planning stage. So you're doing MPC, but there seems to be human responses can be quite varied. So can you comment a little bit about the branching factor? How do you branch across? How deep do you go? And I don't really understand what you quantify success or the short one, whether the shortest heuristic is the best one. So maybe you can talk a little bit about that.
Yeah, so once you have this model that predicts human responses, but during training we only train on successful sessions. So sort of the model only learns to imagine or successful chat sessions, and we just want a successful chat session that's short, and that directly optimizes for the language model to quickly get to the right answer while also listen to what the human response is doing. As opposed to predicting the correct answer directly, sometimes you'll see that it will try to guess what the human wants, but doesn't quite listen to the feedback. As for branching factor, I mean, we're only sampling, I think, 8 or 10 rollouts at a time, and then picking the shortest one. That's all done in parallel, so it doesn't really impact the time.
Okay, let's thank the speaker again. Next, we have natural language can help bridge the sim-to-real gap, presented by Albert.
Roboticists dream of unboxing a robot that works in one target domain, such as our home, and can learn new tasks with few demonstrations. Several approaches tackle this goal. One trains only on target domain data, but these policies require a lot more than just a few demonstrations, which can be infeasible for the end user to collect. Another approach is to collect even more data on many different real-world domains to generalize to the target domain, but this can be prohibitively expensive. Yet another approach is to construct a hyper-realistic digital twin of the target domain to leverage abundant simulation data to complement scarce real-world demonstrations. However, it is extremely engineering intensive to do system identification to match a sim environment to the real environment, and real-world physics can be hard to faithfully simulate. Even after all these efforts, a sim-to-real gap would still exist. Can we avoid system identification by using natural language to bridge a wide visual sim-to-real gap? Language could help extract abundant information from simulation data when learning from a few real-world demonstrations. We propose doing so by learning domain invariant representations through natural language. Say we have a sim and real image from pick and place with very similar language descriptions. We want to learn a domain invariant visual representation space such that the embeddings of these two images are pushed together so that the policy head can predict very similar actions for both semantically similar images, namely to open the gripper to place the object. Conversely, if the sim and real image have very different language descriptions, then we want the learned representation space to pull apart the embeddings of these two images so that the policy head can predict very different actions for these two images. We adopt the pre-trained fine-tune paradigm where we first aim to learn a domain-invariant visual encoder for sim and real images. For each image language pair from simulation and real, we encode the images through a learned CNN to get image embeddings, and we encode the language descriptions through a frozen LLM to get language embeddings. We experiment with two pre-training variants. A, regression-based, where the CNN must predict the language description embeddings from the image observations with a learned linear layer. However, we thought that this might be too strong of an objective, which is to predict the exact embedding value. So we additionally experiment with a more relaxed form of a variant, B, distance-based, where the CNN must predict image embeddings such that the sim and real image embedding distance matches the corresponding language embedding distances. In the second step, we take the visual encoder from the first step and make it the backbone of our language condition policy. We cast sim-to-real as a multitask learning problem between many sim tasks and one real target task. We add adapter modules to process the language instructions, add a policy head, and do BC. We experiment with 3 different task suites of varying difficulty and time horizon, including one with a coarsely simulated deformable wire. Our results are as follows for 100 real-world trajectories. The x-axis represents the 3 different task suites, and the y-axis is the success rate. In shades of blue are the non-pre-trained baselines, which is just a randomly initialized BC policy trained either with or without simulation data. In red is MMD, which is a classical popular domain adaptation method. In shades of green are prior works in large-scale vision language representations, CLIP and R3M. And in shades of gold are R methods 2 variants, which outperform all the baselines. So these results, especially on WireWrap, demonstrate that language can bridge wide sim-to-real gaps even when there are deformable objects. We also decreased the number of real-world trajectories we have. So this is at 50. Our method still outperforms all baselines, and the same holds at 25 real-world trajectories. These are some rollouts of our policy doing two-step pick and place, and some failures, which include not being able to start the second step after finishing the first step. And this is our policy wrapping wire, and some failures involve grasping imprecision and premature gripper opening. So in conclusion, we see that language can bridge wide sim-to-real gaps with domain invariant visual representations with 25 to 100 real-world trajectories, and our method enables leveraging abundant low-fidelity simulation data to improve sim-to-real transfer even with deformable objects. Thanks for listening.
We have questions. Well, people think I would start with one. Over here. No, I have a question. Okay, fine.
Okay.
Yes, so basically you say like natural language like helps us to bridge the gap and everything, but like in the language annotations that you've used, you've actually been quite explicit, like place the caret on the yellow mat, so you gave a lot of additional feature information, whereas natural language usually, like in day-to-day communication, is much more context dependent. So have you actually evaluated or have you checked if even like a more natural description is like, just pick it up or place it on the mat or put it aside, if that would also help you, or do you have to be detailed, fine granular in your language descriptions?
Yeah, thanks for the question. So I might have a couple of points on this. The first one is the kinds of language that you're suggesting, which is like very language-based action primitives, like picking up something or placing something. I want to draw a distinction between that kind of language and language that we're leveraging, which is language descriptions of the images themselves. For example, where the robot is in relation or in spatial relation to the objects on the scene. So there's a distinction between what the robot is doing in terms of language in the form of action and language in the form of descriptions. So in language in the form of actions, we have seen prior work that was presented at RSS, including RTH and Yell at Robot, which do something that you suggested there. But we kind of focus on, we want a visual representation, and so we use language that is at the spatial level. And the second point I'll make is that we don't need the language to be extremely fine-grained. We do have a study on that in the appendix of our paper, how fine-grained do the language annotations need to be, and we see that you can shrink the granularity of the language to quite a sharp degree, and there's still benefit to be extracted when we do sim-to-real transfer.
Okay. Any more questions? Okay, cool. Let's thank the speaker again. Okay. So the final talk today is POCO, Policy Composition from and for Heterogeneous Robot Learning, presented by Yilan.
Hi, yeah, my name is Yilan. I'm going to present POCO in place of Leroy, who can't unfortunately come due to visa issues. So our paper, POCO, is about policy composition, and it's a modular framework towards imitation learning from diverse sorts series of data. So the motivation of our work is this idea of compositionality. So imagine if we had learned a policy for a task of using a wrench to twist something, and we learned a second policy for the task of using a hammer to hit a nail. What we can do as humans is we can actually combine these skills together, and then we can solve a new task, such as using a wrench to hit a nail. But this is not something that we can really do with current generative models, even in the image space, where if you ask a text-to-image model to make an image of a wrench to hit a nail, it's unable to do that. So right now, existing generative models have some difficulty in really composing different series of information together. So in this paper, we study a variety of ways in which we can compose policies, where the policies can be trained on different sorts of data, ranging from simulation, human demonstrations, or real robot teleoperations data. So we can take models trained on each of these separate areas and combine them. We can also take models trained on different series of tasks, such as cutting something or arranging something. And we can also take models trained on different modalities. So we can have models trained on RGB images, on depth point clouds, or on tactile senses. To compose different policies together, we use diffusion models. So diffusion models have proven to be very powerful in both image synthesis, as well as in high-dimensional action spaces. So we'll illustrate how we can really compose diffusion models together across all of these different domains. And overall, and we'll show a couple different types of composition. So we talk about how we can really compose policies with different behavior constraints across different domains, as well as across different modalities. And the overall intuition of how we compose these models is we can really interpret diffusion models as learning a type of energy landscape. And if we view each diffusion model as representing an energy landscape, the denoising model is just a gradient, and we can add the denoising predictions to solve for something that combines two constraints. So what this means at the implementation level is you have a normal diffusion policy, but now for your denoising prediction, you simply add the denoising predictions of other models. And that ends up composing the two policies together. And we show a variety, and there are a variety of ways to compose these policies, which we'll talk about a bit more in detail next. So the most basic type of composition is behavior level composition. So you can take the normal denoising function that you've learned for a particular policy. You can just define another cost function, such as collision avoidance or smoothness, and you can just take the gradient of that constraint and add it with a denoising prediction. The second form of composition is task level composition. So here, if you have one denoising model for solving one task, another denoising model for a separate task. And it turns out you can, again, compose the denoising functions in a particular way to combine the strengths of those. And finally, if you have models for different domains, one for human demonstrations, one for real robot demonstrations, you can, again, add the denoising functions to combine the information across these two different domains or different modalities. And this gets you a policy that combines all those strengths. And then we train our model on a variety of different data sources, ranging from real-world data, simulation data, and as well as from teleoperation data. So the first experiment we show is how composition can allow you to generalize the scenes with distractors. So here, our approach when we compose a model training simulation in real world is able to successfully solve the task. And we can also see that we can also use this composition to be able to more finely cut an object. So here we combine a task level model for cutting with an unconditional policy model. And finally, we also find that this type of composition allows you to generalize at the domain level, as well as the task level quantitatively. So composing models allows you to more accurately solve a variety of tasks. And so overall, we've introduced a modular framework for learning policies. So instead of trying to learn one giant monolithic policy, we can instead compose a set of policies trained on different domains. And we find that that is able to solve a variety of dexterous tasks. And please visit our website for additional information. Thanks.
Do we have questions? Yes.
Hi, thank you for the presentation. Can you elaborate a bit more on how you ensure that the different policies do not start conflicting with each other and fighting for what the robot should do? Thank you.
Yeah, sure. So we assume that each of the policies are multimodal. So if they're multimodal, then if one policy, so you take the intersection of the two modes. So as long as both of the models have some support where they both have high likelihood, then you wouldn't have these contradictory behaviors. Otherwise, we don't really do this in this paper, but one way that you can avoid having too much conflict between two policies could be to have each policy operate over different parts of your input, like output. So like one model might be operating over the next couple actions, another one could be operating over like a single action or like across a chunk of actions, so that they have less conflicting gradients.
Do we have more questions?
Cool, yeah, great talk. I just wanted to clarify something maybe I misunderstood. So do you have a different model for each like kind of embodiment, like a human model and a robot 1 model, robot 2, and what does that model like mean? What does the gradient mean?
Right. So we can get yeah, we do have separate models. So let's say we have a model training in simulation and one model training in the real world. So the real world one could be trained through teleoperation, and then the simulation one might be trained with depth point clouds from data generated in simulation. So both models define like a probability distribution over possible next actions to solve a task. So now if you multiply these distributions together, you have a new distribution that tries to both take the information you've learned from simulation as well as the information you've learned in the real world and tries to combine both of them.
Okay, if we don't have any questions anymore, I think we're actually perfect on time. So thanks, Yulun. And that concludes the invitation learning session. Thank you, everyone. But stick around because we now have the awards, I believe.
Yes, thanks everyone for staying until the very last, but very important as well, task for the conference. For the main part of the conference, we also have workshops afterwards. And this is our awards presentation. Great, and awards at RSS obviously depend on the reviews. The process depends critically on the feedback of the reviewers, of the area chairs, then it goes to the program chairs, Dana and Jiantien. They generated a large list of candidates that then it's passed to the award committee. And I would like the award committee to join us on stage. They're going to handle this process. Tim Barfoot, Dong-Hyu Lee, Michael Milford, and Hyun-Dong Oh. And I'll give it to them at the stage.
All right, we're getting near to the end of the conference. So first of all, I just want to tell you a tiny little bit about how the awards process worked this year, especially if you're asked to do it in future years, and then describe the process that will unfold today. So first of all, you get an email from the program chairs before the conference, and it's with mixed feelings that you get that email because it's a great honor to serve on the awards committee, but they're also telling you that none of your papers are an awards finalist at the same stage. So you get to know ahead of everyone else that you are not in the running. The committee takes the role very, very seriously. We've invested a lot of time in the lead up to the conference and especially during the conference. We all know intimately the effect that awards can have on a research career, and so we've taken it very seriously. At the same time, if your paper is not an award finalist this year, don't stress. Just having your paper at RSS is a great achievement. And if your paper is a finalist but doesn't happen to win, again, that's an incredible achievement, and maybe next year will be different. How did the process unfold? Well, every time you do this process, it's a little bit different. This year, we got handed a shortlist, or more of a long shortlist, based on the reviews. And our initial job was to pick finalists for each of the categories, and in some cases, shift papers between categories as well. For example, of shifting categories, if a paper was in the running to be a finalist or a winner in 2 categories, and it would win in one category. In some cases, we'd consider leaving it in that category and removing it from the other. We took a little bit of a socialist approach to handing out awards. Obviously, everyone can do it a little bit differently. During the week and before the conference, we read all the papers, we watched the presentations, we asked questions or watched how the presenters responded to your questions, so thank you for asking lots of hard questions. We also went and saw demos, and sometimes we quizzed the researchers individually. In some cases, we did check the reviews again, but the reviews were primarily used to arrive at that initial long list. We're looking at a variety of factors: impact, elegance, clear, fresh, appealing new ideas, extensive experiments, compelling capabilities, and wonderful execution of the research. And also what was really new compared to recent papers from the same group. Obviously, this is subjective. There's no absolute quantification of awesomeness, but this was discussed at length. Each of the committee members scored a large number of papers out of 10. We provided a lot of commentary, which informed the discussions that we had during the week, and there was at least 2 committee members scoring each paper. These scores were normalized per reviewer. This was so if one of the committee members was a little bit cranky, we could add the scores together in a relatively fair way. They were combined, and then we ended up with an initial ranking of the papers. This is where the most discussion occurred. So we had an initial ranking of the top papers. We were discussing primarily how many finalists we thought there should be in each category, and the ordering of those finalists as well. We didn't just look at the top ranked papers, we looked at what would have been near misses, and we argued both ways in terms of would this paper actually be higher up on the list based on our subjective impressions, not just the numerical scoring, and that process went on in a number of meetings. This also occurred for the top-ranked paper. This had, I guess, in each category, this had the most discussion. Again, we played it off against other plausible candidates for the award. So what was the outcome of all this? We ended up with 10 finalists across 4 categories and 1 winner in each of the categories, and that's what we're going to get into now. So just to describe the process, I'm going to call the finalists in each category up on stage. I'll read out the paper names and the authors. Please hold your applause until all of the finalists in a category are on stage. We'll then announce the winner. One of the program committee members, award committee members will present the award. There'll be a photo, you're the photographer, and then everyone can exit the stage for the next category and pick up an envelope to keep your certificate protected on the way home. All right, without further ado, let's move on to the first category, which was outstanding demo paper. So, as you saw in the email, the 2 finalists in this category were Demonstrating Crop Follow++, Robust Unacademy Navigation with Key Points by Arun Sivakumar, Matthias Gasparino, Michael Maguire, Vitor Higuti, M. Akkal, and Girish Chowdhury. If anyone from that team is here, please come up on the stage, hold your applause. And the second best paper finalist was Demonstrating Agile Flight from Pixels Without State Estimation by Ismail Geles, Leonard Bersfield, Angel Romero, Jexu Jing, and Davide Scaramuza. So if we can have a representative from that second team up on the stage. You can all come up if you want. You don't have to be just one person per team. And congratulate the finalists. And it appears that the winners are not just getting a certificate, but also some little Dutch knickknacks as well. All right, and so those are the finalists, very well deserved, and the winner is Demonstrating Agile Flight from Pixels Without State Estimation. All right, so let's pause for a photo with the winners. All right, fantastic. And don't forget to get an envelope on the way out. All right, awesome. All right, the next category was Outstanding Systems Paper award. And we had 2 finalists in this category, so again, please feel free to come up as I read out your paper name, and everyone from the team can come up. The first was Universal Manipulation Interface in the Wild Robot Teaching Without in the Wild Robots by Cheng Chi, Zhenghie Zhu, Shuo Pan, Eric Casono, Benjamin Birchfield, Xian Feng, Russ Tedrake, and Shuran Song. Do we have a representative from that team? Please come on up. Ooh, okay. And the second finalist was Chronos, a unified approach for spatiotemporal metric semantic SLAM in dynamic environments with Lucas Schmidt, Marcus Sabati, Yun Chang, and Luca Carloni. So I've definitely seen some of them around the room. Please come up on the stage. I'll take a finalist photo. Awesome. And the winner is Chronos, the unified approach for spatiotemporal metric semantic SLAM in dynamic environments. Take a photo. All right. The third category, which had a large, long list, so this probably had the most work put into going down to finalists, was Outstanding Student Paper. So we have 3 finalists in this category: Dynamic On-Palm Manipulation via Controlled Sliding by William Yang and Michael Poser, Agile but Safe, Learning Collision-Free, High-Speed Legged Locomotion by Taran He, Chong Zhang, Wenli Xiao, Gunkei He, Changli Liu, and Guanhua Shi. And finally, Screw Mimic by Manual Imitation from Human Videos with Screw Space Projection by Arpit Baheti, Priyanka Mandikal, Ben Abatamateo, and Roberto Martin. So if we have any of the representatives from those 3 finalist teams, please come up on the stage. We'll take a few photos. Oh, wait, more photos. All right, and the winner is Dynamic On-Palm Manipulation via Controlled Sliding. Awesome. And now, for the lucky last category, we have the Outstanding Overall Best Paper finalists. So we have Advancing Humanoid Locomotion, Mastering Challenging Terrains with Denoising World Model Learning by Zheng Gu, Yanzheng Wang, Jian Zhu, Chenming Shi, Yangjian Gao, Yichen Liu, and Jianyu Chen. We have Real-Time Anomaly Detection and Reactive Planning with Large Language Models by Rohan Sinha, Amin El-Hafasi, Christopher Aguirre, Matt Futa, please come up on stage, you can come up as we go, Matt Futa, Edward Schmerling, and Marco Pavoni, and Configuration Space Distance Fields for Manipulation Planning by Yinming Li, Zhumin Qi, Amireza Razmaju, and Sylvain Kalinon. So if we have any representatives from any of those 3 Best Paper finalists, please come up on stage. And the winner is real-time anomaly detection and reactive planning of large language models. All right. Thanks so much for staying with us, and I'll hand it back to our chair.
And thanks to Michael and the awards committee for doing a great job and staying on time. Thank you all on behalf of the entire organization committee. See you at the workshops, and then see you in Los Angeles next year.